from the University of Seville, but I'm here in a stay for 2 months. And first of all, let's get out of the way the usual questions that I always get. First of all, I'm going to talk about machine learning, like quantum, no quantum machine learning algorithms, but just classical machine learning applied to the study of quantum phase transitions. Now, this is, as I said, a classical machine learning method, and it will be applied to a classically simulated quantum system, which, the next step that we want to do is actually put it in a, in a quantum computer like the IBM or something. But for the moment, everything is classically simulated, and we are trying to study, the quantum phase transitions of a quantum model, but using machine learning as a helper, let's say. So first of all, I will start with this example, which is actually the second one that I've done, but I think it's more simple to understand. We have a model. In this case, is a version of the Liebking model where we use an additional anharmonic term. But as you can see here, there are 3 boxes with colors which are trying to bring your attention because those are the things that matter. Only matter that we have some Hamiltonian, okay, that has 2 control parameters that maybe in an experimental setup we can control really well, or maybe we don't really know how well we can control them, but probably there are some lasers that we can tune the frequency or something, but we are not assuming that we can control these parameters, that we can fine-tune them to get the quantum phase of the system, because if we can already know in which quantum phase we are just by looking at the parameter, because as I will show you here, the lambda parameter is going to be the order parameter for our quantum phase transition. So, well, a quantum phase transition is similar to the standard phase transitions, but we are here controlling some parameters and with a model, with a system that behaves quantum, and it's not like any change of temperature or pressure or anything like that. So in this case, what is happening is that we are first in a symmetric phase, and when we are crossing here in the 0.2 lambda, when the value is 0.2, that's the critical point, where, as you can see here, I don't know if it's very clear, but we have like some blue lines, some red lines. Well, those are the energy levels that here they become degenerate, but by pairs. We have here the odd and even parities. Then they become degenerate, and at this point is when that happens, and that is the quantum phase transition. Now, the anharmonicity term that we have added changes this separatrix into this kind of 2, but that only will affect the excited state quantum phase transition, which are the ones that happens for higher energy levels. In this case, we are only going to study the regular QPT, which is the one for the ground state, okay? So we want to be able to see this, but as easy as possible. We want to be lazy, so we want to be able to extract that information with as little effort as possible. So we are going to try, even though it is something that is happening in the ground state, we will try to be able to extract the information with another initial state that maybe is more easy to prepare, like, for example, a very generic state like all spinors have. Then we will have to deal with the Trotter error, because our simulation, since there are some terms that do not commute there, we will have actually the product of 2 exponentials, which is, since they do not commute, are not equal to the exponential of the sum. So there will be an error here, which is like that you can see the evolution through the Trotter approximation, and we have to deal with that in some way. We will try to find the most, let's say, comfortable way to solve that problem. And then, instead of doing like before I've showed you the whole spectra of the system, or having to do some full state tomography or something that is more costly, we'll try to be able to extract that information with an easy to measure observable, like simply the expected, like an expected value of an operator, or for example, this correlation function that we define like here, like that, which is the correlation function between two sides, and it is in principle something that is easy to measure experimentally. And then, of course, quantum simulations, they have very big restriction on the number of qubits that we can be working with. It has been shown in several papers that for some quantum simulators, which are usually of the order of 16 qubits or something like that, you can see the quantum phase transition. So we're trying to do with something that is a little bit less than that, maybe for 8, maybe we can do for a system as small as only 2. So let's try and do that. Yes?
Why do you see that this is an easy to measure observable? Right? Because you have an observable which is not local, right? Sigma 1 set, tensorial product sigma 2 set, right? That's not local, right?
If I have to be completely honest with you, I've been told that this is easy to measure. It is not easy to measure. Okay. Well,
you have to do something to measure it.
I mean, you have always to do something, but the thing is that you don't have to. I have been told that it's less complex than some other things that you need to do to extract the quantum phase transition. Yes. Yeah.
Yeah, my question is related to the simulation. So you have used the trotter method, but why do you consider this to be the easiest one?
Well, you will see that later because you actually don't have to correct for the trotter error.
But have you considered any other method that, like linear combination of unitaries or like quantization?
No, in this case, no. But the thing is that the trotter, using the trotter expansion, actually, what will happen, I will show you later, is that the trotter error actually helps you into classifying the quantum phase of the system. So I haven't tried with something else because this is actually not only not a problem, but actually something that helps in this case.
Yes. The phase transition is a property of the Hamilton.
Yes.
Not necessarily of the unitary. So why is it that in the unitary you have the time?
Sorry?
You have the time as a parameter.
Yes.
That has no role in the calculation of the phase transition.
Well, because what we were trying to do here is using some time dynamics, like trying different observables and how they behave over time to try and extract the quantum phase transition information from that time dynamic of the...
I understand this point. My question is then you can take t as small as you want as a parameter also, because it doesn't play any role in the phase transition.
No, like it doesn't play a role in the phase transition.
It helps you in order to reduce the trotter errors, because you can reduce so this t is very, very small.
But then we cannot use the time dynamic of the parameter, because if we take too little of time, then it won't really change in that time enough. It will?
No. But,
like we did. I mean, in principle, we have taken like the idea that this observable that we are going to be measuring will change significantly in time.
You are not starting against state, you are starting with an arbitrary
Yes.
state.
Yeah, that was part. We are not going with the ground state, because if we are with the ground state, then nothing changes. Okay, so with these ideas, what we want to do, like I said, we are going to measure an observable, see how it behaves with time, and we can get, for example, here 3 lines are, first for lambda equal 0.1, we see that this correlation function has like this form here, in the critical point it has this form, and then when we are in the other phase, the broken symmetry phase, it has a different form. And the idea is, well, the forms, like the way they evolve is different, but can we say that this kind of evolution corresponds to a phase, this kind of evolution corresponds to another phase? How can we distinguish between them? So that can be, like in some cases, where like my teachers we're dealing with this in a specific case where this correlation function became maximal, like it went to the maximum amplitude exactly in the critical point. When the phase transition happened, it became maximum. But in this case, for example, doesn't happen that, that doesn't happen, and with different alphas, like the things start to become a little bit different. So how can we actually, we cannot really quantify that easily those things. For this is where we use the machine learning algorithms, because they are really good at distinguishing different forms. So what we're going to do is use, in this case, I tried many different things, but a convolutional neural network worked really well, which convolutional neural networks are like a lot of the time are used to classify images. So we can do the same, but in one dimension. We are trying to classify signal forms, let's say. So what we are having here is like we have our parameters that will give a unique form for the Hamiltonian, which has a unique evolution, which will give us a unique correlation function, a unique shape of the correlation function. Now, like I said, all of this is simulated classically. So because we know from mean field theory, we know how this specific model behaves and where the quantum phase transition is located and everything. So we can produce data and then train, because we know the labels that correspond to the data that we have constructed. So we can train our convolutional neural network and then give more data, which we don't give the model, we don't give the label. So the machine learning model, the convolutional neural network, doesn't know what is supposed to be. Then it will predict a phase, and then since we do already know, we can check if it predicted correctly. And when we give the data, it predicts something like this, okay? Which is like in blue are it colors in blue the points that correspond to the symmetric phase, and in red the points that correspond to the broken symmetry phase. It's a bit more easy to see when you collapse all of this with alpha, because alpha doesn't change the critical point. So we can see that the convolutional neural network always predicts 0, which is symmetry phase, for the points that are below the lambda, the critical point, and then it predicts 1 for the points that are at the other side. So it is working really well. We can even see that here there is a little bit of uncertainty, which makes sense because, well, in the critical point, both phases are going to coexist. So the thing is like, okay, this theoretically works, but in our system, we are not going to have this exact evolution because, as we said, we are going to have a trotterized evolution. So let's see how well it works with a trotterized evolution. Well, the idea is that this correlation function is close enough to this correlation function because this evolution is close enough to this evolution, so that when you go to the convolutional neural network that has been trained with this correlation function, when it sees this, if it's close enough, it is going to be able to classify it. And it kind of works. Yes?
Sorry, how do you compute the exact evolution?
Well, because we know, like the system that we are using is exactly solvable. This one, I believe is analytically solvable. The other one is just exactly solvable, but not analytically. But
so
I mean,
you don't have to use always trotter. You have an exact.
Yes.
Okay.
Yes, this is just to check that it works. In other cases, when you are forced to use some specific cases of. Yes.
You can do it always numerically, the first one and the second one, numerically, but with trotter, right? Which is the strategy you will apply in a real system, in a simulator.
Yes. So, like the system, we know it, but when you apply it in a simulator, you have the one block, then another block that you have to simulate. So, in that case, you have the trotter. Yes.
Yeah. So maybe you want to talk about later, but so this is the only type of error you have considered, the trotter error.
I will add more errors later. Yes. So with the trotter error, yes, another question.
I'm curious about your definition. For instance, you just check the C. Why don't you choose this OTOC or the Yakov parameters to set this criteria? Why you only choose this correlation function?
we tried with several, we tried with other things. We had interest in the correlation function because in a previous work, in a previous study from my teachers, they saw that it was a useful proof for the quantum phase transition of a certain model that I will talk about later as well a little bit. So they saw that, they saw that this correlation function was useful for that. So we tried to apply the same kind of correlation function to other models. It didn't seem that it was going to work as well, but using the machine learning models, we can see that it in fact still carries the information of the quantum phase transition, and we can extract it. So that was the idea. Like the task that they gave me was, can we get the quantum phase transition with this correlation function? And I was like, yes, you can. So, like I said, when we have the Trotter error, well, the quantum phase, it still kind of predicts pretty correctly, but you can see that it is like the quantum phase transition shifts to the left, so it's not as accurate. So the idea now is, well, we can make the Trotter, yes?
Which is the N for this simulation and the previous one?
Sorry?
The capital N for this simulation and the previous one.
Okay, these ones are with n equal 8, with a system size of 8. So we are doing this with a system which is pretty small, which, for example, I was going to talk it later, but since you asked, let's get that out of the question. In this case, for example, like I said, you know the quantum phase transition from mean field theory, but you have like a infinite n. But in this case, you can see that this is for a system size of n equal 100. You can already see that, if you zoom, in this case, since it's not zoomed, you don't see it that well, but if you zoom, you can see that effectively the ground state and the first excited state, the energies become degenerated at the critical point. So the more the n, the more close it happens to 0.2. So 0.2 is the solution in the limit. But the idea here is that if you have only a system size of n equal 8, the problem that you will have is that this degeneracy will happen later. It kind of shifts to the right because, well, you have finite things going on, so it's not as exact because technically this is only exact for the limit of infinite n. But the idea is that even in those cases where if you did the spectra, you wouldn't precisely see where it happens, you can train the neural network to predict it correctly in the point where it would happen for infinite n. So in these cases, these are for n equal 8. And I was going, this is kind of okay, but it's not really that good because it's shifted to the left and we want to be as precise as we can. So the idea is we can make this arbitrarily precise by taking more and more Trotter steps, but more Trotter steps means that you are going through the quantum gates of your circuit more and more times. So then you are adding the infidelities of the quantum gates. So you are taking away the Trotter error, but you are adding other errors, which can be a problem. So the thing is, well, it is true that this can be approximately the same as this if we give enough Trotter steps, but if we don't want to do that because we are lazy, as we said previously, we can realize that, well, these parameters will give a unique Hamiltonian that will have a unique exact evolution, but it will also have a unique Trotter evolution that we know because, well, there is an expression for it. So this correlation function will also be unique and will be related to the lambda. So technically, it still has the information of the quantum phase of the system. So what I tried next was, well, I will train my convolutional neural network using the wrong evolution instead of the correct one, because the wrong evolution, even if it's not showing the actual target system, it still has the same properties regarding to the parameters, so regarding to the quantum phase transition. And when we do that, when we train with the wrong evolution, then when we test with that evolution, which is the one that we would presumably measure in a quantum simulator, in a real quantum simulator, well, we actually get a perfect prediction. It even looks like it's better than the regular one. And this was at first a bit of, well, are you sure that this makes sense? Because it doesn't really look like good that this one has more precision than this one. And the thing is that it actually does. So that's one of the things. The Trotter error not only is not a problem, but it's actually a helpful thing. So in this case, I added a noise. Well, in this case, I added just a random noise, just like a proof of concept. The random noise is quite big, so in this, like the random noise is of the order of 0.1, so and the correlation function goes from 0 to 1, but for example, in this region here, it rarely goes above 0.3, so it's kind of like a big error of 1/3 of the signal. So of course, when we do it with the exact evolution, the signal is destroyed, and the convolutional neural network, which is trained with the not noisy signal, is not able to extract the quantum phase transition or the quantum phase at all from the noisy signal. But when we add the Trotter error, the evolution changes, but changes in a way that the features that let the convolutional neural network extract the information are enhanced. So the error makes those like the evolution more like, let's say, big or more spiky, maybe, I don't know how to say it. But the thing is that the signal becomes like, the features become enhanced. So when we add the noise, it changes less. It's like the Trotter error supersedes the other error that we are adding. Therefore, when we train it with the Trotter error and we add a noise, the convolutional neural network is still able to predict the phase correctly, even though we have this big error. And in fact, if the Trotter error is having a positive impact, well, why correct it at all? Why add any amount of Trotter steps other than just one, which is we are not doing the approximation. We are just doing the product of the exponentials. And you can see that it works even better.
Yeah, my question was about that the Hamiltonian is time independent.
Yes.
Okay, so then two Hamiltonians, not connected.
You have actually.
So the Trotter is with one Trotter step, and at which order do you make the factorization of the two parts of the Hamiltonian?
So are you asking for, like, is the first order Trotter approximation?
So
if that was what you're asking?
If you have A is equal A plus B, you make exponential
Yes.
of A, exponential B.
Exponential of A, exponential of B. That's the case, yes.
Could you go back to the Hamiltonian that you're using?
This?
Yeah.
So you have, you can add like these two terms, but then you cannot add the third term because they do not commute. So you have, like, for example, the C for one side and the X on the other side. Yeah, what?
Just a dumb question. What's N? What's the number of qubits?
N is the system size.
And why do you, because that's a scalar, right? Why do you have to include it? It's not an operator, right?
Well, that is actually, I don't know how it's called, that when you take the, this is written in a bit of a weird form, because this is actually a diagonal matrix of, like, there is an identity there that I'm not putting.
Yeah, but you don't need to consider it.
The thing is that there you have this J, which in the case of maximum symmetry that you can take without losing generality, it turns out to be n half. So okay, yeah, that's the case. It's okay.
Can you go to the Trotter when you are describing the Trotter convolution?
Well, I didn't put it here, but here I would have the JC, like the JC plus the JC squared. Like there is a term with JC squared, a term with JC, and then a term with JX squared.
Okay, so the HK corresponds to each of the terms.
Yes, it would be H1 would be the c plus the c squared, and then h2 will be the x squared. Yeah. I didn't put all the things because I didn't want to take too much time. So I was just like, well, there is a trotter error, and then, yeah.
But in the correlation function, you have 8 qubits, or 8 dimension 8. What do you, so I don't understand. N, what is, it's n qubits or dimension n?
The dimension, like for the n, the big N, is the dimension of the system, like the system size. The thing is that for a system with size 15, you need 16 qubits because you have the Hilbert space is plus no, the Hilbert space. I'm now making myself confused, but yeah, for a system size of 15, you need 16 qubits. Yeah, and you have 16 different energy levels.
Okay, but then when we are calling sigma set 1 and 2, what is 1 and 2?
Those are like they would be the sites. For example, for a system of size 8, you could have like, yeah, sorry, I glossed over that, but you could have like the correlation function between sites 1 and 2, 1 and 3, 1 and 4, or 2 and 5. It's like if you have sigma C1 product sigma C2, for example, right? So that would be this. The thing is, I glossed a little bit over that because since we are using an initial state with all spins up, any correlation function between any two different sites will be the same. So this could be like AJ, so the sites AJ. Okay. I don't remember where I was. Yeah, with the noise. That, yeah, in fact, using the trotter expansion, even if we are adding this kind of error and we are not technically representing the exact evolution that we want from our target system, the information from the quantum phase of the target system is still there, and it actually helps by minimizing the effect of other additional errors. Like I said, I don't still know, because we haven't tried in an actual quantum simulator, how the noise from the quantum gates could affect it, because that's not random. But we presume that it's going to be smaller than this noise that we have been adding, because, for example, in this case, we are only taking n equal 2. So we are taking a really small system of n equal 2, so it has very little amount of quantum gates. So the total fidelity of the circuit, we are expecting it to be quite high, and it shouldn't affect that much. So the trotter error, the problem, like the trotter error should help minimize the effect of the quantum gates. Yeah, Ruben.
I guess you have tried with other noise levels and the results are the same.
I put this particular level of noise because this is the first where, you know, having the full trotter error only has this small effect here. If you start adding more, then you can still get it pretty good, but I thought this was the most easy to visualize, that this one is completely destroyed. If you get less, well, this one still kind of works, a little bit worse. So this is like the good level to see that it is destroyed. It kind of works. It works perfectly. But yes, different noise levels give, you know, there is a correlation between the amount of noise and how good it preserves the breakthrough. Yes.
Would you say that this result is very specific of the model you are working with?
No.
You say no.
You will see now with another model. Like the second part is another model with 5 different quantum phases.
Okay, but it seems that in some way, so the result that the trotter at the n equal to 1 only keeps the phase, let's say this quantum phase.
Yeah, well, first of all, the number, like the system size, I've checked without taking, don't think about the trotter error thing for the moment. Without taking that into account, simply changing the size of the system, this convolutional neural network is still able to predict the phase correctly. I didn't see any visible effect regarding system size. So for a system size of 2 or a system size or 8 or a system size or I believe I only did up until 12 to make calculations fast. but it didn't really change. Like the predictions were, I mean, they were not 100%, but it was like 99.8%. And the small variations can be given like due to, well, simply that it is an stochastic method and it's not, you are taking random test data that is not always going to be the same. So the small variations seemed to be about that. And well, since you can go as little as n equal 2, well, there's no need to see if it's a little bit more precise to n equal 100, because it still works really well. And like I said, yes, this is a system that is simple. It only has, either symmetry phase or no symmetry phase. Well, what happens with another model, which was actually the initial interest that we had, because my teachers were doing with the Agassi model. Like the Agassi model is a nuclear model, like a model is in nuclear physics. They were doing it for a system size of 4, but in that case, it kind of you could kind of simplify it to kind of the same problem as before, because it collapses into only 2 different phases, symmetry and asymmetry. But for example, for a system size of n equal 8, which was my initial job to do, you have a phase diagram like this one, really pretty, with 5 different quantum phases, which, well, those are the phases. I don't know the actual, particularities of these quantum phases. I just know that they are there. And the idea is, well, can you do this thing, like use the correlation function for a system which is much more rich in phases than the previous one, and use then some machine learning algorithms to learn to predict that phase? And the thing is that you can. So here, kind of the same. In this case, the initial state that we were taking, it wasn't. I tried with also all spins up, and it kind of works pretty well. But in this case, particularly, I cannot tell you why. It worked better with an initial state that was half of the spins up and half of the spins down, and then I tried with like 16 different correlation functions, and this one was the one with the best results. So there is a little bit of cherry picking there, but we were just trying and testing a little bit of trial and error to see what worked better. And this was also the first work, so even though it's a bit more complex, so that's why I put it in the second part. Since this was the first work, it had a little bit more of trial and error. So again, we are taking the correlation function. In this case, we are measuring the correlation function, and then we change one of the 3 parameters. In this case, instead of lambda and alpha, but only a lambda was an order parameter. In this case, we have 3 order parameters, which are this big lambda, sigma, and chi. And then we start put the 2 of those remain constant, and we start moving one of them to see, if the correlation function presents any kind of maybe not discontinuity, but maybe some kind of effect that happened exactly here, which would be the quantum phase transition, in this case, plane. But I mean, this is the correlation function on one side, this is the correlation function on the other side. These ones are much less clear to just see that. I mean, they are different, but in the other case, you could see, well, maybe when this happens is when this is in one phase, but in this case, you see that they are different, but you cannot really say, oh, yeah, this is definitely one of those 5 phases. So the idea is well, how can we learn to classify that? Well, we don't need to learn it because we can have the computer learn. And in this case, it's kind of the same, okay? I just put it in small. I don't know why the chi just went away, but well, you have the 3 parameters, which have the Hamiltonian will have a form for all those 3 parameters for each combination. Then you have a unique evolution, which in turn gives you a unique correlation function over time. And then in this case, instead of 0 or 1, it gives an array, which the probability that it predicts for each of the different 5 phases. So you will have an input like this, and the output will be something like that, which in this case, I'm pretty certain this is this specific phase, the BCS, the Barden-Cooper I don't remember the names. They are pretty difficult. But yeah, so doing this, in this case, instead of the line like we had before, I have these graphs with colors, which, the bar represents the certainty that the model has that the quantum phase, like the correlation function, corresponds to that specific quantum phase. So in this case, it's like it is almost 100% sure that it is the symmetric phase. Then in places like, well, this one is almost sure, but it's a little bit uncertain that maybe it's another phase. And what we get, again, like you can see how in all these cases, because the parameters are scaled properly so that it happens just at the point 1, which is the one in the middle. You can see how in the middle the predictions change from one color to another. So it changed from one phase to another. Yes?
So when you say that you are doing trotted, where do you divide the Hamiltonian? Which?
Yeah, we have the group that only has parameters. Well, in this case, it's a little bit different because in this case, what we did was all of the operators, we expressed them in terms of annihilation and creation operations for fermions. Then we applied a Jordan-Wigner transformation. And at the end, you had like 138 blocks of products of Pauli matrices. And well, each of the products, well, some were depending on sigma x, sigma y, others sigma y, sigma x, something like that. And then I just brute force and calculated the commutators for all of the terms, and so which was the best way of grouping them. And in this case, you have like 8 terms that do not commute with each other.
Okay.
I know that's probably not the best way to do it, but that was my first month in the job, so I was like, well, I guess I just compute the commutators. But yes, in this case there are 8 different non-commuting terms. Yes.
Did you use Jordan-Wigner or didn't think to use another mapping?
I used Jordan-Wigner because it was the one that they told me this is the usual way to do this. So I learned how to do that and I just applied it. I know now that there are other ways maybe that you can do the mapping that it can be better. I don't know the specifics, but in several papers that I've been reading, they still use Jordan-Wigner, so I guess that's pretty good. Oh, there is a problem that you just...
There exists a problem.
Okay, well, with that, you get, again, like I said, you can see, this is similar like before, we are at one phase, then it has a little bit of uncertainty, then it predicts the other phase, so you can see the quantum phase transition. Here are only some examples that I tested with, straight lines through several of the phases, but other cases present similar results. They are actually also pretty good at predicting not only the phase, but where the transition happened. And in most cases, again, the Trotter error actually helps predicting the quantum phase. It makes it so that it's more sharp, the change. And in this case, not only we try to predict the phase, but we also try to predict the parameters. Given a certain correlation function, if you can extract the parameters, well, the parameters automatically, because in this case, the system again, so automatically gives you the knowledge of which quantum phase corresponds to those specific parameters. So I did that as well, and you can see that, it predicts it pretty correctly. In this case, you only need to look at the y-axis. The x-axis is just the different points, the different cases. So you can see that we are taking, in this case, like steps, changing the parameter 0.1 in each let's say in each point, and the mean square error of the predictions that is less than that step that we are taking, so it predicts pretty correctly the parameter. This is only one example I did with the other parameters. One of the parameters, which is the lambda, is the one that predicts a little bit worse. I think it's for the way that the quantum phase transitions happen. So that one, if you check the correlation functions, when you move upwards, they change really little. So it's a little bit harder to look at both and see what is what. And well, this is just like a fun example of how this graph kind of gives you an idea of how well will it predict the parameter, because in this case, since it has some uncertainty of which phase it is, when it predicts the parameter, it also predicts it a bit like way up that it should be, but still within like below 1, which should be the correct phase. So yeah, it not only can classify like a quantitative, not a qualitative thing like the phase of the system is this, it can also give you a qualitative value of the parameters that correspond to that specific point. So in cases where you can maybe, like I said, you can change the parameters, but you don't have a super well-defined quantum simulator where you know exactly how much you are changing one parameter but changing this laser or this other laser. So it can give you also that information. Well, that's the main idea. So we try to be lazy. I need to think about this correlation function thing, because I was told that was easy to measure, so I didn't look into that.
No,
but
it's not especially difficult, but not straightforward.
Okay.
To do something.
Yeah, so the idea is that it was because for quantum phase transitions, usually they go for full state tomography, which is quite costly. So they normally want to have some observable that you can measure in the simulator and then extract the information from that. And that was the idea, yes.
Well, in any case, if you assume you can do each block of the trotter decomposition, I guess you can assume that, okay, you can do the operation needed for measuring that kind of correlation. Because they are more or less equally difficult or easy, right?
Yeah, like for example, in this Lipkin anharmonic model, well, the idea was to use a digital analog simulator with the blocks with C squared being analog block, the X squared analog, the C squared analog with a rotation, and then the other one just single qubit rotations, for example. In the case of the Agassi, it's a little bit more like complicated, but in principle, since you can do the Jordan-Wigner mapping, well, you have everything in terms of product of Pauli matrices, so you can just do it. The idea was in trapped ions, which you can do all of those products with a single laser in all ions, and it was good to be scalable and everything. But yes. Well, that was it. It was a little bit longer than I expected, but yeah. I'm always happy to answer questions if I can. And if I know.
So my question is, how would you employ this, like in a case in which you don't have the information already of where is the...
That's always the usual question is like, okay, this is very well, but you already know the system, so why? The idea is like, well, you can see these quantum phase transitions in a quantum simulator, which is not like with an infinite system size, because the theory to get this information is quantum like mean field theory, so you have to go to the thermodynamical limit and everything, and in a real case you cannot do that because you have a limited system size and everything. So the idea was, well, let's prove the theory by measuring something that we can actually measure in a current quantum simulator, but also I've tried and failed many times to use unsupervised machine learning methods which do not require previous knowledge of in this case, the quantum phases. So it do not require previous knowledge of the system. And sadly, they didn't work. I tried like probably 30-something different approaches, and they work just a little bit better than randomly putting the things. They are a little bit better than random, but they are not really suitable to get the quantum phase transition, because they usually, the problem is like, since near the quantum phase transition, the correlation function in this case, or the expected value of another operator that you might be measuring, they will be really similar. So with unsupervised methods, it's like, well, they are really similar, so I will put them together in the same group. So you don't really get to see that clear transition between one phase to the other.
So then you say that the use is like to just to do experimental proofs in a simulator or something.
Yeah, like the idea is that in a quantum simulator you don't usually see very clearly the quantum phase of the system if you want to do studies of the quantum phase of the system, because since you are like mostly because you're doing dealing with a small system size, but also it's also like a way of saying, hey, if this information is here, we can extract it with a, like maybe you cannot visually see it, but if you can extract it with a machine learning algorithm, that means that the information is there. So maybe, like, I am still hopeful that I can find a way of extracting that information without having to know it beforehand.
In this case, it would be like you have the simulator, you know the control parameters, you know what should
Yeah.
be.
So the idea is, yeah, that you don't have to prepare a specific initial state. You can have a kind of generic initial state, and the phase transition, you are able to still see the quantum phase transition of the ground state using a generic state that is not the ground state or agent state of the system or anything. You don't have to worry about your simulator needing to be really precise regarding, for example, the Trotter error, and maybe some other noises that you will get can be diminished by the Trotter error in case that you can still see the quantum phase transition.
But it looks to me like you are teaching the neural network to say to what you want it to say, depending on what the simulator is outputting, right? Because you know
Yes.
what phase it should be, and then you teach
Yes.
the network, now you have to say this, now you have to say this other thing.
Yes, that's
a proof that there is indeed a phase transition in the system you are looking at.
I mean, the proof is theoretical. Yeah. The thing is that
yeah, I mean as an experimental.
Well, in principle, if the computations that you do theoretically say, like, you predict with quantum, like, mean field theory.
Yeah, of course, I believe in the theory.
No, the idea is you know that from the theory. Yeah. Then you present a way of, well, if that is correct, then this will predict the things correctly. And then you measure the thing, and you see if it, in fact, corrects the things correctly.
Okay.
Yes?
I have another question. Have you tried to retrieve the limit in which the Trotter steps goes to a really high number and like to reproduce the exact dynamics with noise?
So, in like...
Yeah, you have shown this one, and in the exact case, have you tried to increase the number of Trotter steps?
Yes, like if you increase the Trotter steps further, they, like, in this case, if you just increase the Trotter steps, they will start beginning to look like this, because when you increase the Trotter steps, it becomes more and more like the exact evolution. And in this case, if you increase the Trotter steps, I mean, here there are only two cases, but you can see that when you increase the Trotter steps, it becomes a little bit worse. What will happen when you have the noise and you increase the Trotter steps, it starts to become more and more, like, you have less Trotter error, it becomes more like the exact simulator, like the exact evolution, so the signal gets destroyed and you cannot extract the information of the quantum system, or the phase transition. Yes?
So then you are not extracting the information from the evolution of that parameter, but from some other function that you have created and that you can operate in a quantum computer, but it's not longer the evolution that gives you.
Yeah, exactly. It's the wrong evolution. It's not the evolution that the target system would actually have.
Yeah, and how can you be sure that this is a general property? Because maybe it's because of this.
I'm not sure that it is a general property, but I've tried in 2 cases and it worked. That's everything I can. I tried in 1 case, it worked, and I'm like, wait, maybe it will work in another case. And in this case, it also works. I have, like, in principle, the thing is that the Trotter error will modify the signal in this case, but in a very specific way that you know, because the Trotter expansion, I mean, there is also an extra error because of in this case, I'm taking only the first order trotter expansion. So, there is an extra error laying around there, but it doesn't seem to have very much effect. So the idea is like, it will change the signal, but it will change it in a specific way that is not random. So it seems like the same way that you can see the shape of this function and know the parameter, you can see the shape of another different function, which is more feature-rich. Like instead of doing something like this, maybe it does this. So it's more like it has more variance, or it has some features that you can see more clearly. So even if it's a different thing, it's still like a unique relation between the parameter and the evolution that you get.
My question was more in the line of not the model that you are trying to analyze, but the initial state that you are using and the model. Because I guess the initial state is very important in this case, because it determines the state, the final state that you are analyzing.
Yes. Like I said, in the first, like in the case of the Agassi model, I tried with different initial states. There is a paper in the archive where there are some examples there, and it performed really similarly. But it is true that it seems that some initial states, it is an initial state correlation function pair that you can, because depending on the initial state, the correlation functions can be different. Like in this case, since they are all spin up, then the correlation function between 1 and 2, 1 and 3, 1 and 4 is going to be the same. But in other cases, that's not the case. So the pair of correlation function initial state does have an effect, but it's hard to, let's say, quantify how much it affects. Like there is some case which is going to give a little bit better results, but in general, it works. Like it works with, like in the Agassi model, for example, which is in the one that I did more tests, always with a 98% probability or more. It was like with a accuracy of 98% or something like that. It's always around that order. Then, well, in that case, if you take the correlation function in the z-axis, because you can take it also, for example, with sigma x. So, like that's just a observable that we are defining. You can take the correlation function between different sites in different axes. And for example, in the case of the x-axis, doesn't work as well. So it depends in the kind of symmetries that the system may have and everything. So the thing is looking which is the better one, and then you train with that, and when you do the measurements or what you have to do, they have to do it with the same. Because, well, like I said, in these cases, since it's an old model, well, you can try the different cases and see which is the best one. But yeah, the hope for this is to be able to extract the information about quantum phases without needing to know beforehand which are the quantum phases. There are some other promising papers. For example, there's one in which they did something similar. No, it's not exactly the same, but they imagine that you have something like this, right? But then at this point, for some reason, something like this happened. At this point, the neural network is really uncertain of which is the quantum phase. Well, that happened in a different experiment. They were trying, like, it was a similar thing, but the ideas were different. And the thing is that with that, they kind of discovered that there was probably, you cannot say percentage, but there was probably a third different quantum phase that they didn't know about from theory. So since at that point, the machine learning algorithm didn't know which phase it was, well, they can kind of deduce that probably there is a third different quantum phase, that is a different quantum phase transition that is happening there, and that it has maybe different properties. So they went on to study that. I believe they realized that in fact there was a third quantum phase. So in a case like this, maybe you can you could happen to have something like that, where at some point the model doesn't predict correctly, and maybe this because, well, at that point it's not behaving like any of the two previous phases that you know. Yes.
For me, it wasn't clear in this specific slide the combinational level. The CNN from the first case, that one,
Yes.
is trained with the exact evolution, right?
Yes.
The second one, going up, is trained with an amount of trotted step which is fixed or not?
Yes, in this case it's with you know, a trotterized evolution with 4 trotted steps, and then this one is the same but only with a single trotted step, which is
It's CNN is trained with a specific amount of
yes.
and then the noise is the same for 50 cases.
The noise is the same for every case.
Then I don't understand how come that with one trotted step you get like the perfect thing, and with the and in the first case the exact one is completely messed up.
Like I said, the thing is that, for example, in this area for the exact evolution, the correlation function, imagine that it does something really I don't know how to say, like a smooth or like a slow variation, something like this. But when you add the throttle error, it does something like this, and then suddenly does like it and goes up. So when you add the error, this going up like that, it is still like in a way, let's say like with intuitively, you see that going up at the end, you are able to realize, oh, it's going up at the end. I don't know what's happening here, but it's going up at the end. So it's probably at this side of the phase diagram, right? So it's something like that what's happening. Well, that's what I think it's happening because I've checked the correlation functions at the different cases, and that's what I can extract for it. But the thing about neural networks is that you don't know what they are doing. They converge into a set of weights. You don't know what those weights mean. Like in cases like this, it's a really small convolutional neural network, and that means that it has like 1 million different weights. Like not exaggerating. That's 1 million is really small. So I cannot really say which each of the weights is looking at or what is actually really happening exactly. But that's what I think is happening. So that's what I can tell you.
If we like that in this case with one trotted step is like perfect. The combination.
I mean, it's perfect for the amount of noise. If I increase the amount of noise, this will as well get destroyed at the end. But the thing is that the idea is that since the error is bigger, well, it makes the other errors look smaller.
Yeah.
Basically. Yes. Yes, thanks.
And error, you just put it on top of this correlation function, or
yes. Like this is a really simple thing that I did like last week, which I have the signal, the correlation function, and I added a random noise on top of it. So it's like a simple, little bit naive way of testing it, but well, it clearly shows that it makes it more robust to certain errors that maybe arise. I don't know why it stopped. Okay.
So would you expect, because everything is with n equal 8, all the results that you're obtaining?
Oh, no, this, for example, this one is with n equal 2.
No, this one.
Capital N equal 2, yes.
Okay.
So these ones were, like, I give a lot of different graphs, but I have to choose some of them. So in this case it's with n equal 8. In this case, we are already with n equal 1, n equal 2. And then here what I changed the number of throttle steps to see how it was better. But the thing is that the results for different number of n were practically the same. Like I couldn't say that they were different because the precision was so high that the differences could be just stochastic.
But the problem is that also, I think that the problem of the initial state will become harder and harder when n grows.
Yes.
Because essentially, so what you are doing with evolution is to witness the phase transition when your initial state is evolved through the Hamiltonian towards a high component in the ground state. The ground state is the one that contains information about the
Yes.
but the larger the system is, the smaller, exponentially smaller, the projection of your initial state with respect to the ground state is going to be, in general. So you will need longer and longer times in order to transform your initial state into a high component of the ground state.
Yeah, that's actually true. The thing, I believe, yeah, it's true that I haven't checked with larger n because, well, since it seems advantageous to have smaller n and it worked for the initial n that I tried, then I started working downwards. It is true that it's probably going, like, it might be like increasing the number, the system size, and having a larger n might result in worse performance of the neural network, maybe, or the need for larger times to the.
Yeah, the problem is going to be about.
Oh wait, no, but the times here are like are scaled with n in this case. So like this thing that I'm showing you here, like is with h bar equal 1, and then the t is technically scaled with n. So for larger n, you would need an actual real time that is larger. But in what I'm doing here is like, since it's a scale, so it's for the for relatively the same amount of time. So yeah, okay.
What? Last question, because we are already over our time.
Questions that I can ask.
Yeah, we can talk right now if you want.
Okay.
I don't want to keep you hostage.
Any short question? No? Okay, let's start.
Thanks.